Hi, and welcome to the lecture on inference and regression. Before we begin talking about inference, let's just revisit our model so that it's fresh in our mind. Our model was that the response, yi, is the intercept, beta naught, plus the slope, beta 1, times the predictor, x1, plus an error term. The error term, epsilon I, is what we're labeling it. We're going to assume is normally distributed, mean 0, with a variance sigma squared. For the time being, we're going to assume that the true model is known, and this will be the basis for most of this class. I'm going to assume that you've seen some amount of statistical inference previously, so you know what a confidence interval is and what a hypothesis test is. Let's also remind ourselves that the intercept is estimated at y bar minus beta 1 hat x bar. And our beta 1 hat is the correlation between the predictor and the response multiplied times the standard deviation of the response over the standard deviation of the predictor. So let's talk about how we can perform statistical hypothesis tests about our parameters. Let's review a couple of concepts from statistical inference. First, statistics of the form theta hat minus theta divided by the standard error often have the following properties. First of all, they're often normally distributed. And for finite samples, if we replace the variance with the estimated variance, they often have a t-distribution. And we'll see this is true in regression context under the assumptions we've made. This statistic can be used to create hypothesis tests of theta being a particular null value versus one of the logical alternatives of it being less than or greater than or not equal to this null value. Or we can create confidence intervals of the form estimate plus or minus a relevant quantile times the standard error, where Q is the relevant quantile, and we always take the 1 minus alpha over 2 quantile. For example, if our alpha is 5%, so we want a 95% confidence interval, we take the 97.5th quantile. And this is either going to come from a normal distribution or a t-distribution. So hopefully none of these facts are news to you after having had the statistical inference class. In the regression case, with IID sampling assumptions for our normally distributed errors, inference will follow along these lines very similarly to what you saw in that class. And we're not going to cover at all asymptotics for regression analysis, but suffice it to say, it's not mandatory for the errors to be Gaussian for our statistical inferences in regression to hold. You can appeal to large sample theory, though it's a little bit more complicated. So the variance of our regression slope is actually a highly informative formula. This is variance of beta 1 hat, and it involves two things. How variable the points are around the true regression line, sigma squared, and how variable my x's are. Now I think the numerator, how variable the points are around the regression line, I think it's somewhat understandable as to why that we would get better estimates of our regression slope if that were smaller. However, it's maybe less intuitive to understand why we want more variance in our predictor in order to get lower variance in our regression slope. But let's draw some pictures. If our regressors, our predictors, are all packed in very tightly, closely together, then it's clear we're not going to estimate a very good line. It could sort of bend around that cloud of points very easily and get equivalent fits. On the other hand, if we spread our x's out, then we'll get a better fitted regression line. We'll get a lower variance for the slope. Now it turns out the lowest you can make that variance is to push half the observations to one end and the other half of the observations to another end. However, you're banking quite a bit then on having a line in between those two because you haven't collected any data to evaluate that property. Here I also give you the variance of the intercept. It's maybe a little less informative because intercepts are often a little less of interest than the slopes. But nonetheless, it has this form right here that we can calculate and write down. In both these cases, we replace sigma squared by its logical estimate, the 1 over n minus 2 times the sum of the squared residuals. We covered that in the last lecture. It's probably not surprising that our slope or intercept estimate minus the true value divided by their standard error follows a t-distribution, and it has n minus 2 degrees of freedom. And so this can be used to create confidence intervals and hypothesis tests. And we'll go through some examples here in a couple of slides, but first I'm just going to show you that all of these results exactly hold, and it's what R is reporting. Okay, let's go through and just demonstrate that the formulas I'm giving are exactly the formulas that R is using when it performs its calculations. So I'm going to use the diamond data set, and that's in the using R library, so I'm going to load those. Define y, x, and n like I always do with this data set, so I don't have to type so much. My beta 1 is the correlation between the y and the x times the standard deviation of y divided by the standard deviation of x. And my beta naught is the mean of the y's minus beta 1 times the mean of the x. My residuals are my response y minus the predicted values, beta naught plus beta 1x. So here I've just carried the subtraction through. There's my residuals. My estimate of the standard deviation around the regression line, the variability around the regression line, is the average of the residuals, except remember we're dividing by n minus 2 instead of n, and to get it to be a standard deviation rather than a variance, I'm going to square root it. There's my sigma. That's my estimate of sigma from the previous several pages. My sums of my squares of x's is just the numerator of the variance calculation, but let's just do it directly. It's x minus its mean squared, and adding those up. So let me get that. And then my standard error for my beta naught for my intercept, if I just simply plug into the formula, there I've written it out. And my standard error for my beta 1, which is I think the more useful and mentally important formula to commit to memory, is the sigma, the variance, the standard deviation around the regression line, divided by the sum of the squares of the x's, the sum of the squared deviations of the x's around their means. Okay, there we go. There's the standard error for beta 1. I'm going to create the two t-statistics, which if you're testing a hypothesis that beta 1 is 0 or beta naught is 0, then that's just going to be the estimate. Here's my estimate, divided by its standard error. And so we don't have to subtract off the true value because the true value is assumed to be 0 under this hypothesis. And so for my beta 1 hypothesis, it's going to be beta 1 divided by its standard error. And then I'm going to calculate my two p-values. Again, if you've taken the inference class, then how you go from a t-statistic to a p-value should not be a great leap. But in this case, it's going to be twice my t probability, where in both of these cases the estimates are larger than 0, so I'm going to look at the probability of being this statistic or larger, and I'm going to double those two t probabilities. And then I'm going to create my coefficient table created manually by me without having done any LM or any built-in higher level R function. And I'm going to give it its row names and its column names so that it looks like R's output. And then now I'm going to show you the easy way to do it. Okay, so here let me print it out. There it is printed out. And then now I'm just going to do fit LM, my response Y is a linear relationship with my predictor X. And then I'm going to get the summary of the coefficients. You'll see everything is exactly the same. So if you didn't follow all this, it's not too big of a deal. I just wanted to show you, for once, that the formulas that I'm giving you are exactly the right formulas, and we verified them computationally by checking them out on a data set. Maybe check them out on another data set just to verify for yourself. Let's go through getting a confidence interval. So my fit, the variable fit, was the output of LM. Let's see what happens if I type summary fit. You get the full output from LM. So it gives you facts about the residuals, it gives you the coefficients, the estimated coefficients, the standard errors, the t-values, and the associated p-values. These are all for test of whether or not the intercept is 0 or the slope is 0. Now, of course, a 0 intercept may not be of interest, but almost always a test of a 0 slope is of interest. But it also gives you the residual standard deviation, the degrees of freedom, the R squared, the adjusted R squared, which we'll talk about later on in the class. Let's go ahead and generate our confidence intervals for our intercept and for our slope. So now I've assigned that summary, the summary from the LM statement, to an object in R, but I just wanted the table part, so I'm grabbing the just the coefficient. So it's right here, see, I'm just grabbing the coefficient table. So let me just print out that variable just to show you what it looks like. It's just the table part, just the estimates, the standard errors, the t-values, and the p-values. Okay, so our confidence interval is just going to be estimate. So here's for the intercept, estimate plus or minus the 97.5th t quantile with the degrees of freedom. Just to make sure I get the degrees of freedom right, so I don't even have to think at all, I'm grabbing fit $ degrees of freedom, and then times the standard error. There I'm grabbing the standard error. And then I'm doing it for the slope, which is in the second row of the first column. So the slope estimate plus or minus the relevant t quantile times its standard error, which is in the 2-2 cell of this table here. And then the slope is going to be interpreted in change in Singapore dollar price per 1 mass increase in carats, the unit for the predictor variable. But I might want it for a 0.1 increase because, as we mentioned earlier, looking at the data, a 1 carat increase was kind of a big increase. So why don't I divide my whole interval by 10? So let's run both of them and particularly focus in on this latter one, the confidence interval for the slope. So it's saying with 95% confidence, we estimate that a 0.1 carat increase in diamond size is going to result in a 356 to 389 increase in price in Singapore dollars. Prediction is a central concept for the data scientist. In fact, we have an entire course, Practical Machine Learning, on advanced prediction techniques. However, regression and generalized linear models, which we're going to cover later on in the class, are some of the most core techniques for performing prediction. They often produce very good predictions, they're parsimonious and interpretable, and as an added bonus, you can get inference on top of your predictions without doing any sort of data resampling. What I mean by inference is we can get predictions and then say, for example, confidence intervals around our predictions to evaluate the uncertainty in those predictions. So that's very easy in regression and pretty easy in generalized linear models, and quite difficult in some more advanced machine learning algorithms. You may have to do data resampling or something like that. So let's just talk about prediction. We might want to predict the response, which might be the price of a diamond, at a particular mass in carats. Or we might want to predict a child's height for a particular value of the parent's height. The obvious estimate in both cases is just take our x naught, our predictor value that we want to predict at, either mass or parent's height, multiply it times the relevant estimated slope, beta 1 hat, and then add the intercept. But if we want to be good statisticians, we need to evaluate some uncertainty in that prediction, so it would be nice to have a prediction interval. There's a small intricacy in that there's a distinction between trying to predict at the line, predict the regression line at a particular point, and trying to predict a future y at that same point. Those are two different ideas. I'll describe that in a picture in a slide, but let me describe the formula first. What we have here, and it makes sense that our prediction variance first relates around how variable the points are around our regression line, sigma hat. And it makes sense that that would be involved in our prediction error. However, here we have this term 1 over n. Okay, that also kind of makes sense. Typically our standard errors decrease at some rate 1 over square root n, so a 1 over n in a square root seems kind of reasonable. If we're predicting a new y, then we have this added 1 out front, so we get a wider interval if we want to predict a new value at a specific point versus trying to predict what the regression line is at that point. So we'll talk more about that later, but let me also focus on this very end term that is in both equations, x naught minus x bar divided by the sort of the top of the variance of the x's. consider the numerator of this statistic. Our prediction error is going to be the lowest when x naught is equal to x bar. So our prediction variance is going to be the smallest when we're predicting at the average price of a diamond, or at the average mass of a diamond, or at the average height of the parents. So that's one thing to notice. The second is this summation xi minus x bar squared in the denominator. That's basically how variable my x's are. The more variable my x's are, the smaller this term becomes and the lower my prediction error is. So again, not unlike our slope estimate, where the more variable our regressors were, the less variable our slope estimate is, the same thing happens in our prediction error here. Okay, so let's go through some pictures so we can try to solidify these concepts. But this is an essential part of using regression for prediction, that you get easy and convenient prediction uncertainty associated with your parsimonious predictors. So let's generate some prediction intervals for the diamond data set. And I'm going to go through the code here, and actually most of the code is just a little bit of data wrangling to get it in a format that's friendly for ggplot, at least insofar as I know ggplot. So I'm not going to go through this too carefully, because after having had Roger's class, you're all better at this than I am. So let me go through just the most relevant part of this code, and that is the predict function right here. So here's my predict function, and I'm going to give to my predict function the output of LM. For a lot of prediction algorithms, especially linear models and generalized linear models, but other things, random forests and other things in R, the predict function is a generic method that applies to them. So I'm going to give it the output, in this case, of my LM. And then I want a nice denser grid of x values to predict at for my plot than the observed data. So I'm going to give it some new x values. And then here I tell you I want a confidence interval, not a prediction interval. That's R's code for saying I want the interval around the estimated line at that particular value of x, not for a potential new y at that particular value of x. If I want an interval for a potential new y at that particular value of x, I change the interval equals confidence to interval equals prediction, which I do in this line below. So here I'm going to run all of the sort of data wrangling code, and then let me go through my ggplot. I like to do this just because I find ggplot a little bit confusing at first, but once I've gotten used to it, I like it quite a bit. And once I've done this data wrangling, then notice this some kind of complicated plot only takes a couple of lines. So I'm going to start my ggplot. I'm going to add a ribbon, and the ribbon is going to have two parts because it's going to be filled by the interval type. So the blue one will be a prediction interval, and the kind of salmon colored one will be a confidence interval. And then I want my fitted line added, and then I want to add the observed data points. Now my observed data points aren't in the data frame that I used to create the ggplot, so I have to give it a new data frame and a new aesthetic command for this particular layer. And then let me do my plot, and then I'm going to switch windows to a large window with the plot. So here's my plot, and again the blue is the prediction interval. This is for predicting a new y, and the salmon color is for a prediction of the line at those particular values of x. And so what you'll see is the prediction for a line, a so-called confidence interval for the R command predict, is much narrower than the prediction interval. And here's how I like to think of this, because if you're confused, and we know this to be the case from the math, right? There's that 1 plus for the prediction interval, and there that 1 is missing for the confidence interval for the line. So here's the way I like to think about this. Imagine if I collected an infinite amount of data at all different values of x along this line. Well, then I would pretty much know the regression line exactly. And if that were the case, I would be extremely confident about predictions on the line, where the line was at a particular x value. So as I collected more and more data, that salmon-colored confidence interval would get narrower and narrower around the line to the point where it was just the line itself. And that's good. That's what we would expect to happen. That's just the idea of statistical sampling working. On the other hand, the prediction interval, there's variability in the y's that has nothing to do with how well I estimate beta naught or beta 1. And in fact, imagine if I were to just give you the correct beta naught and beta 1s. There would still be variability in the y's because there's that error term. And so if I want to predict a new y, there's some uncertainty that just doesn't go away with better estimation. It's sort of inherent in that there's leftover residual variation from my regression line. So that variability will be ever present in the prediction interval, and that's why it's 1 plus. That's why that 1 shows up in the equation. It doesn't go away with n. It doesn't go away as I collect more x's or anything like that. It's inherent, and that's why the prediction interval has a certain amount of width that's never going to go away. The last thing I'd say, you can see it probably, I think, a little bit more in the confidence interval here than in the prediction interval, but that both of these get narrower toward the center of the data cloud and then get wider as you head out into the tails. And that's just simply saying that we're more confident in our predictions the closer we are to the mean of the x's. Now, because of that 1 plus, it means maybe less for the blue color than it does for the salmon color, and you can see it more clearly with the salmon color. So that's why it pinches in a little bit, and that makes sense. If we were to go well beyond where we collected data, then these intervals would really become a lot wider, which is what we'd want, because we would be extrapolating. We would want to predict where we did not collect data. So on the next slide, I just summarized those points, but I think that's enough to get you started on inference from regression. And now we'll move on to some more complex topics in regression and generalize to where we have more predictor variables and so-called linear models.